Muda o som aqui. Tá.
Okay? My name is Benedito Bonato. I'm a professor at the Federal University of Itajubá, in Brazil. And I'm going to present this topic, optimum time step size and maximum simulation time in EMTP-based programs. This idea of trying to find a time step size optimum for EMTP-based programs were based in previous work done by Professor José Carlos Goulart de Siqueira from Unifei, and with some cooperation from Professor José Martí, Dr. Holman, and Dr. Gomel at the University of British Columbia in Vancouver, Canada. So we start with an introduction. We discuss about the ranges of time constants in a generic circuit. They are not really time constants, but you calculate as if they were, if the combinations of R, L, and C were either series or parallel. Then a first approach to find an optimal delta T and Tmax is applied for some test cases. And another alternative is calculate the space state matrix from the conductance digital matrix of an EMTP type program. And having that, we can calculate the continuous time eigenvalues of a given system during the digital time EMTP simulation. Then, if we have all the eigenvalues, we can precisely calculate the delta T and Tmax. And this is a technique that can be improved and applied for offline or even real-time simulations. So EMTP uses the time step size as a measure of the accuracy of the simulation. The delta T is chosen by the user, and usually the user doesn't know what is the ideal delta T for simulating a specific phenomenon. So if you use a smaller delta T, you have more precise, more accuracy in the simulation. But if you do not choose the size of delta T correctly, the results you're going to have might be wrong. So the motivation for creating a kind of empirical algorithm to automatically develop a first initial proposal for the selection of delta T was done by Professor Goulart in Brazil. So the Nyquist theorem states that the maximum frequency you can see in a signal sampled with a sampling frequency Fs is Fs over 2. So if you sample a signal at 1000 hertz, 1 kilohertz, you can only see phenomena up to 500 hertz. For EMTP simulation, a rule of thumb is trying to relate the maximum frequency with the Nyquist frequency in a way that you take 1/50 of the Nyquist frequency as the maximum frequency you're expected to see in the simulation. And with that in mind, it's easy to calculate the delta T. Delta T becomes 1/10 times the maximum frequency you expect to see in a phenomenon. So there is a range of frequencies that different phenomena in a power system can provide. So how can you choose accordingly the delta t. If you know the phenomena, more or less, you can set a delta t and run the simulation, and then you reduce the delta t and compare the results, and then you reduce again the delta t and compare the results. So it's a trial and error approach. For new users of EMTP type simulation, this might become a burden, and that's why this work might help. So how can we do that? Well, one idea is, since we are not actually calculating the time constants, we're not calculating the real eigenvalues of the system, but we can play with the data provided in the input from the user. So you can assume that all elements are either connected in series or in parallel. If they are all in series, then you have a maximum values for resistances and inductances. Capacitors, you have a maximum value when they are associated in parallel. Then you add capacitors. Whereas if we have all elements connected in parallel, you have minimum value for resistors and inductors. But when they are in series, capacitors in series, then you have the minimum capacitance. Having those maximum and minimum values, it allows you to calculate what would be the time constants when you have an RL circuit or RC circuit, or even when you have an RLC circuit. You can calculate the natural period of oscillation, which is the inverse of the frequency of natural oscillation of the system. If you have transmission lines, you can take into consideration the propagation time of that line, because in that case, the selection of the delta t has to be smaller or equal to the minimum propagation time. Otherwise, you're not able to see the reflections of voltage and currents from the sender and receiver of the line. So, if you have all those time constants, calculated values, you can organize those values in an ascending order from the minimum to the maximum, and then you can select the delta t. For example, taking 100 of the minimum value in this vector of time calculated values, right? And the maximum simulation time could be, for example, 5 times the maximum time constant in this vector. The reason of using 100 instead of 110 is because when you compare the digital solution with the analytical solution, in the transient period, in 0 plus, you're going to have almost exactly the same magnitude in the digital simulation and the analytic solution. So this is empirical. We found that 100 is a conservative choice. You can increase the delta t later on if you wish. But as a first guess, this is a good guess. 5 times the maximum time value in the vector t is more or less intuitive as well. So steady state is reached when you have 5 times the time constant of an RC circuit, for example, or RL circuit. So then you have a window to see the whole transient. And this is more or less important based on this experience the user has on running EMTP simulation. For example, if you take this simple RLC circuit with those values, of course we only have one R, one L, and one C, but we could play with this and just as an example, and calculate the time constant or the time values we have TL, L over R, T, C, R times C. The TL minimum is L minimum divided by R max. The TL max is L max divided by R min, and so on. And then we organize those numbers in a table. And with those sorted values in ascending order, we select the minimum and take 100. And that gives us an idea what would be an optimal delta t. If you take 5 times the maximum value in this table, we ended up with the tmax of 1.11 seconds. Running this case shows us that we can fully see the transient period for voltages and currents, and especially for voltages across the inductor. At 0 plus, the value that we can see in the graph is exactly as if we were calculating the analytic solution of the system. That's why 1/100. So voltages and currents are completely simulated with those values. So it would be difficult to guess that Tmax should be 1 second and delta T 250 microseconds initially, just based on the RLC values. So usually people would set delta T 1 microsecond and Tmax 100 milliseconds. But 100 milliseconds is not enough to see the whole transient period. In this case, we have a lightning phenomena with many, in a substation, with many bus bars represented as transmission lines. And we also have a surge arrestor here, and the transformer is represented here by a capacitance in parallel with resistance. So the main issue is, for a case like that, if we apply that algorithm, we ended up with this table of values, and we can select the delta T and the Tmax accordingly. Tmax is in the order of 216 microseconds for a phenomenon that is very, very fast. And the delta T results, in this case, very, very small. This is an empirical algorithm. We need to evaluate. Eventually, we might find that there are other ways to organize and calculate these time constants instead of this. But if we use a delta T of 0.1 microseconds, 0.1 microsecond is the minimum propagation time in the circuit. So that is enough to represent the reflections of in the transmission lines. I cannot use values bigger than 0.1 microseconds. It has to be smaller than that. But eventually, we do not need to go to nanoseconds to represent this phenomenon. So eventually, there is opportunity for improving this algorithm when we have a circuit with transmission lines. But nevertheless, running the case, you can see the transient phenomena. The voltage builds up, the currents due to the lightning currents, traveling along the substation. And in this case, we're running up to 0.10 microseconds. It's a very fast phenomenon. But you don't see how large the voltage would be if you don't have an estimate of Tmax, the maximum time. When you use these Tmax and run 200 microseconds, you see that you were looking only in the first beginning of the transit. So running it up to Tmax, you can see the transient and the steady state. Then you see the maximum values that are going to reach after the lightning hits the tower and propagates along the substation. So using Tmax is equally important as finding an optimal delta T. Both of them are useful for engineers when running EMTP simulation. And you can see that in that case, if I don't use a surge arrestor, voltage builds up to 1.48 megavolts. With surge arrestors, especially in the transformer, which is node 4. The voltage is limited to 700 kV. If we don't have certain resistors, it goes above 1 megavolts. That would eventually cause damage to the transformer. Well, another alternative is try to find the continuous time eigenvalues directly from the digital EMTP formulation using the G matrix or the history source. And so how we can calculate the space-state matrix, the continuous time A matrix, from the digital modeling G conductance matrix. So Dr. Holman developed his PhD thesis on this under Dr. Martin's supervision, and they come up with a very nice formulation for that. So you can get the digital space-state matrix using the combination of vectors that take into consideration the G matrix and having this digital matrix, you can find the digital eigenvalues and the continuous time eigenvalues. So from the discrete time state space matrix, we can get the continuous time state space matrix. And then you can calculate the discrete time eigenvalue and eigenvector, and from that you can calculate, having the continuous time space state matrix, you can move from discrete time eigenvalue to continuous time eigenvalue. So having the eigenvalues, you can look into the real and imaginary part, and it's almost straightforward. Evaluates time constant. The time constant associated with this complex eigenvalue is the negative of the inverse of the real part of the eigenvalue. But if you have a real time constant, then it's straightforward to define the delta t, because that's real. That's not a calculated or estimated time constant. It's the real time constant. And then you take the minimum, because your minimum time constant represents the fastest dynamics. Then you choose the smaller delta t that is able to represent the fastest dynamics you have in the circuit. And to calculate the tmax, you take the maximum time that represents the slow dynamics and should be able to see transients and steady state periods accordingly. Mm-hmm. If you take the RLCKs and calculate the eigenvalues, those are the eigenvalues. And we can calculate the period of the natural oscillation frequency we have in the imaginary part of the eigenvalue as well. And organizing this, you can see that we reach for delta t 1 millisecond. We have used 250 microseconds. That was 1/4 of this value. So this is enough. With that empirical algorithm, we have used half of this. But for tmax, we have used 1.1 seconds. And the ideal or the proposed using the real eigenvalues is 1.19 seconds. So for this simple example, the exact solution and the empirical solution, they match. Therefore, in this work, we propose a simple empirical method to estimate the optimal size of delta t, the time step size, and the maximum simulation time to be used in EMTP time problems. This is very important for new users of EMTP as well as for experienced users, since the program may give them the first estimate of what would be the ideal values. And then they can take the decision to use or not that value. But as far as the authors know, we don't have this option. Usually programs come with a predefined value, and that's the value that it's the user responsibility to select the proper time step size. If you have a variable time step size, then this problem is solved. But even in this situation, how to choose, how to move from one time step size to another time step size whenever you cause changes, open or close switches in a system. So you can use the second algorithm, which is exact. Every time you make changes in the system, you can calculate the real eigenvalues, and from that you define the optimum delta t exactly. So this is another alternative that can be used. So this is our contribution. We would like to acknowledge the sponsor agencies of Brazil, CNPq, CAPES, FAPMI, and any search from Canada. Thank you very much.